if you're asked to decide if a function is continuous, then the first thing that you want to look for is, was the function given to you as a piecewise? And remember, those piecewise functions are usually going to be written something like f of x is equal to, and then you got some stuff for x is, and I'll just pretend function there. Let's say for x is greater than 4 and something.
Excuse me?
Yeah.
The green's not showing up too well.
Great. Okay. That was my fear. Let's kill the green. Thank you for letting me know. So first thing you want to be thinking about is that function you've been given piecewise? So if it's something written in this form, or you've got, let's say, some function for x is less than 4, some function for x is greater than 4, there are really two pieces that you're being asked about in that continuity. One is just, what's the domain of the function? So even if something's been given to us piecewise, we want to look at the individual pieces and check for any possible places where something's going to go wrong with the domain. If there's nothing wrong with the domain, so like, are these lines, are they parabolas, right? Are they something that normally continuous everywhere because there are no domain issues? Then the only thing you're checking is, does this meet those continuity rules specifically at 4? But if I give you a function and it's like just a single thing, so if I gave you the function, let's say x plus 2 over the square root of x minus 1, if I ask you where this function is continuous, that's the same question as asking what is the domain of this function. So if I were asked for the domain of this function, I'd be looking at that and saying, oh, I've got two things I need to worry about. I have a denominator and I have a square root. So that denominator piece would tell me that I can't have the denominator be equal to 0. So I couldn't have x minus 1 be equal to 0. And then the square root piece would tell me that I need x minus 1 to be greater than or equal to 0. Taken together, since we know we can't have the equal to part, we could just summarize that as saying we need x minus 1 to be greater than 0, or that x has to be greater than positive 1. I did notice, and so this is usually the case for web work, when you're reporting your answers out in web work, you do need to write them in interval notation, meaning x being greater than 1, I would write as the interval, parentheses, 1, comma, positive infinity. And in web work, you can usually write this out as a word. You can type the word INFINITY, infinity. Yeah. Good times. Let's say that this was a piecewise function, and let me give us a piecewise function just so that we can practice continuity for that and that 3-part rule for continuity. Let me say that I've got x squared minus 3 and 4x plus 1. If I'm checking continuity for this piecewise function, the first thing I want to look at is each of the functions individually, and are there any domain issues? There are not. This is a parabola, this is a line. Their domain is all real numbers. So then the only possible place where we have a discontinuity is happening where the pieces match up, meaning at 4. So I want to check at x equals 4, what's happening? And in terms of our continuity rules, we've got our 3 pieces. The first part says we need f of 4 to exist. Well, in this context, what that means is there somewhere where we are allowed to plug in the 4? And there is, because of that or equal to. So f of 4 is equal to plugging the 4 into that top function. So 4 squared minus 3, that's 16, minus 3, I get 13. That second piece for continuity asks us, does the limit as x approaches 4 for this function exist? Because it's a piecewise function, we're going to check this by taking the limit as x approaches 4 from the left, or 4 minus a little bit. And we need to know, is that the same as the limit as x approaches 4 from the right, or 4 plus a little bit? So if I'm looking for the realm of 4 minus a little bit, then that's going to be this top piece. Because if I was at 4, but I subtracted a little bit, then x is less than 4. So in here, I'd have that x squared minus 3. Coming from the right-hand side, or 4 plus a little bit, that's the other part of our piecewise. So 4x plus 1. First thing we try with any limit problem is to plug the number in. We only have to use all those limit rules if we don't get a number when we try to evaluate it. So here, when I plug in the 4 squared, that's 16 minus 3, and I get 13. And I want to know, is that the same thing we get over here? Well, when I plug in that 4, I'm looking at 16 plus 1, and I get 17. They're not equal, which means this limit does not exist, which also means we can stop there. The function is not continuous at 4. Now for the how do I write that in interval notation? Both of these have a domain of all real numbers. So now we're just going in and we're punching a hole out at 4, because 4 is the only value we want to leave out. In interval notation, that means I'm going to go from negative infinity to 4, union 4 to positive infinity. There are ways that we can find this derivative using the quotient rule, but we can also take this problem and rewrite it so that it looks like numbers times x's raised to powers, and we can just use our power rule. And that's the option I'm going to go with here. Eventually, I want to find the derivative, but the first thing that I want to do is to rewrite it. And I mean to rewrite f of x. So if I think about breaking this apart as two separate fractions, this can be written as x cubed divided by, and since my goal is to make this look like x is raised to powers, I'm going to take that square root and write that as a fraction, or a 1/2 exponent. So I've got x to the 1/2 minus 2x squared over x to the 1/2. Now I can use my exponent rules and fractions, because we love fractions. I can use my exponent rules to rewrite f of x. So this first one, x cubed over x to the 1/2, when I'm dividing two things that have the same base, I'm going to subtract those exponents. So 3 minus 1/2, I would choose to do this as a fraction, because 3 is secretly 6 halves. So 6 halves minus 1/2 would give me 5 halves. Now this next piece, 2 is secretly 4 halves. So 4 halves minus 1/2 is 3 halves. And I'd have 2x to the 3 halves. Now I'm ready to take the derivative, because I was able to rewrite this as a number times x raised to a power. This first one, I'm going to take that 5 halves, multiply it by the invisible 1 in front, so that I've got 5 halves x, and now when I subtract 1 from the exponent, I'm really subtracting 2 halves. So I'm going to get 3 halves. Minus, here I'll have 2 times 3 halves times x, and when we subtract 1 from the exponent, it's going to have an exponent of 1/2. If we want to, here, the 2 times 3 halves, those 2's are going to cancel out, leaving me with a 1. So I end up with 5/2 x to the 3/2 minus 3 x to the 1/2. And that's going to be, I think, the most simplified form for the derivative. So if I think about using our laws of exponents, let's take this piece, for example. I know that one of our exponent rules says that we can combine these by subtracting the exponents. So this would be the same as x raised to this, that got a little messy, x raised to the 3 minus 1/2 power. Well, to subtract those fractions, I would need a common denominator. So I'm going to think about that 3 and give it a common denominator with the 1/2 by multiplying by 2/2. So that would make this x to the 6/2 minus 1/2. And that's where I got that x to the 5/2 power. Same thing is going to happen when we simplify this. That 2 in the exponent, when I do 2 minus 1/2, I'd want to get a common denominator. So if I have x to the 2 minus 1/2, I'd come into that 2 and multiply by 2/2, which would give me x to the 4/2 minus 1/2, and I combine those together to get x to the 3/2 power. I will also say that if you are someone who really hates fractions, well, I hope I can change your mind. But if I can't, and decimals work better in your head, it's okay to do this problem in terms of decimals, right? So you could, just as an alternate approach, think about that instead of saying the 1/2 power, think about that as saying 0.5. And then 3 minus 0.5 would be 2.5. And you could definitely do the whole problem in terms of decimals. There are times in 16b where it's really more important for us to write it as fractions. So I tend to just keep everything in terms of fractions. If I want to find f prime of x, then looking at this, if the only rule we have so far is to take the derivative of something that looks like a number times x raised to a power, then we have to rewrite this first so that we can make it look like a number times x raised to a power. So my first thing here to rewrite it is going to be that I need to multiply this out. There are a bunch of different ways to multiply out polynomials. Whenever I get stuck, I always resort to the box method. So just to recap in terms of multiplying out polynomials, if I want to multiply these two, one option, and you don't have to do this, but one option is to write each of the pieces out. So that 2x squared plus 4x and the x cubed minus 1, to write each of the pieces out into a grid, and then each square in that grid I'm going to get by multiplying the lengths on the edges. So here I'd have 2x squared times x cubed and get 2x to the 5th. And then I'd have 2x squared times minus 1 and have negative 2x squared. For this one, I'll have 4x times x cubed and get 4x to the 4th. And here I'll have 4x times negative 1, or negative 4x. And then I list all those pieces out. So I'd have 2x to the 5th. And if I go in descending order or descending powers of x, then my next smallest would be the plus 4x to the 4th, and then minus 2x squared and minus 4x. Another option for multiplying this out, the acronym that commonly gets used is FOIL. First, outer, inner, last. And I think, and a lot of people use FOIL just to, as sort of a verb, kind of like you might say Google it, right? We're going to FOIL it, and that just means to multiply things out. But technically that acronym FOIL means multiply the first term in each of the pieces together. So when I multiply these two together, that's where I got the 2x to the 5th. Outer, right? So if we're thinking about FOIL, first, outer, inner, last. So that outer, meaning the two outsides, so 2x squared times -1, that gives me the -2x. Inner, so the 2 on the inside, 4x times x cubed gives me 4x to the 4th. And last, the 4x times the -1. Okay. Couple different options for how you're going to multiply that out. But now that it is multiplied out, we're going to take the derivative. So the derivative of 2x to the 5th, 2 times 5, so I'd have 10x to the 4th. 4x to the 4th, so I'm going to take that 4, multiply down in front. 4 times 4 is 16. Subtract 1 from the exponent. 2 times -2 will give me -4. Subtract 1 from the exponent, and I'll be at 1. And then minus 4x, so that derivative is just going to be that -4. And that is my f prime. Now there's a question in the chat, and that's exactly where I was headed next. So the question in the chat is asking, could we also use the product rule? Why, yes, we can. And my h of x is going to be equal to f of x times g of x. So we've got multiplication between these two functions, and h is not a good choice of letter for me. I lied. How about m, because we're doing multiplication? Great. So if I want to find the derivative of my function here, and actually let me make it a capital M just for fun, no reason at all. If I want to find the derivative of m, thinking back to that limit definition, I'm looking for the limit as h approaches 0, and just kind of our normal limit definition. I'm going to erase it in a second, but this would look like f of x plus h minus f of x all over h. But in this case, the function that I care about is actually m of x. So instead of being f of x plus h, this is going to be m of x plus h. And I haven't told you what the functions are, so we're going to work through this generically just with all of the letters. Well, I know that the one thing I do know about m of x is I know it's equal to f of x times g of x, which means that when I'm looking at m of x plus h, that x plus h is what I'm going to have to plug in both for the x in f of x and to the x in the g of x. So this is going to turn into, instead of m of x plus h, this will be f of x plus h times g of x plus h, because that's what I get when I plug in x plus h to our function m. Then we're going to subtract off m of x, and that was f of x times g of x. We're going to put the whole thing over h. And then we're going to say, hey, it's a limit problem. The first thing we try with any limit problem is to plug in 0 for h. But if we plug in 0 for h, we're going to have 0 in the denominator. So we got problems already. And in the top, if I plug in 0 for h right there and 0 for h right here, then I end up with f of x g of x minus f of x g of x. So I would get 0 over 0. But 0 over 0, as an answer to a limit problem, is telling us, go do some algebra. So some mathematicians stared at this for a long time and said, I know what we need to do. We just have to add 0. So the mathematician came along and said, I'm going to scoot f of x, g of x over a little bit. So I'm going to move it over here. And in the middle, add 0. Just going to add 0 creatively by first subtracting off f of x times g of x plus h, and then adding it back on again. So that this part in here equals 0. And certainly if I add 0 to a problem, I haven't changed it. Now the next thing that this mathematician did was to regroup the parts, because having that common denominator of h, we can really think about this as separate fractions, each with the denominator of h. So what the mathematician did next, kept that limit as h approaches 0, but the mathematician kind of grouped this part of it together and this part of it together. And in the end, what that looks like is on the top over here, hold on, I think I'm going to have enough space, we'll see. Might have to start writing smaller. I'm not very good at that. Over here, we've got f of x plus h, g of x plus h, minus f of x, g of x plus h, all over h. And then separately over here, we've got f of x, g of x plus h, minus f of x, g of x, all over h. Now the reason that that's helpful to group it in this way, in this first group, on the top, they have something in common, that g of x plus h part. So if I take that g of x plus h and I factor it out, then this becomes the limit as h approaches 0 of g of x plus h times f of x plus h minus f of x all over h. And in the second part, the thing they have in common is that they both have an f of x. And if I pull out that f of x, if I factor that out, then this would be left with g of x plus h minus g of x, whole thing, over h. Mathematician now looks at this thing and says, hey, we're ready to take the limit, because if I plug in 0 for h now, or if I take that limit as h approaches 0 now, I got to get short. Here, when you plug in 0 for h, we're going to be left with g of x. And this part, we have a shortcut notation for, because the limit as h approaches 0 of f of x plus h minus f of x all over h is f prime. And similarly over here, I've got that f of x, nowhere to plug in the 0 for h, and this piece, the limit as h approaches 0 of g of x plus h minus g of x all over h is g prime of x. That's all in the textbook in case my handwriting got messy, but here's the thrilling conclusion of all of that. If you start off with some function that is two pieces multiplied together, then to get the derivative, we have this product rule, and I'm going to write it in a slightly different order because I'm going to put my derivative of f at the front. But since this is multiplication, we can multiply in either order. 3 times 2 is the same as 2 times 3. So if I swap those, this would look like f prime times g plus f times g prime. And this is our product rule. If I have an f times a g, meaning I've got two pieces, I've got two functions that are multiplied together, and I want to find the derivative, because I have two things multiplied together, I'm going to write those two letters twice. I'm going to write this as f times g and another f times g. Then I'm going to say to myself, because it's multiplication, what usually goes with multiplication, addition or subtraction? Well, it's addition. And then I'm going to chase down the derivative. And what I mean by that is I'm going to take the derivative, but move over one piece when I get to the second piece. So on the second piece, my derivative is going to be on the second letter. Now, the reason I like this is that if I have an f times a g times an h, meaning I've got three things multiplied together, I'm going to write them 3 times. So I'll have f, g, h, f, g, h, and f, g, h. What usually goes with addition, or sorry, what usually goes with multiplication is addition. So I'd have a plus and a plus. And then I'm going to chase down that derivative again. So the first, I have 3 pieces, and the first piece, the first letter gets the derivative. In the second piece, the second letter gets the derivative. And in the third piece, the third letter gets the derivative. So I'm looking at 3 pieces. So I can think about this as like an F and a G and an H. I said H and wrote a G. So I can think about that as like an F times a G times an H. And when we go to take that derivative, that means I'm going to have my 3 pieces 3 times. And if this is F, G, H, the first one gets the prime. And if this is F, G, H, the second one gets the prime. And if this is F, G, H, the last one gets the prime. So when I take the derivative of 3x squared, 2 comes down to multiply by the 3, and I'll be left with 6x. Then I just copy down both the g and the h because they don't have derivatives. I'm not going to do anything except copy them down. Next piece, my f gets copied down because it does not have a derivative, but I do need to find the derivative of g. So here, 2x plus 4, derivative of 2x is 2, and the derivative of that constant is 0. So I'm looking at a 2, and then I'll copy the h down. And I didn't really give myself a lot of space there, but x cubed minus 5x. Here I'm going to leave my f alone. I'm going to leave my g alone. And for h prime, I need the derivative here. So 3 times 1 is going to give me a 3. And then subtracting 1 from the exponent, that'll be an x squared. So I've got 3x squared minus, and the derivative of negative 5x is that negative 5. And again, unless the question explicitly tells you that you need to do more algebra, stop. We took the derivative, quit, walk away. No one's got time to multiply all that stuff out. Hopefully more used to seeing it. Let's start with sine of x. Sine of x looks like this. Only technically sine of x keeps going in both directions, right? So we might think about a chunk of sine of x from 0 to 2 pi, but technically sine of x has a domain of all real numbers, meaning that it doesn't magically start at 0, and it doesn't magically end at 2 pi. It really keeps going forever in both directions. So this is going to be sine of x. Well, one of the things that we might be asked to do in calculus, for sure if you're in Kuba's class, you're going to be asked to do on the next midterm, is to think about this relationship between the function and its derivative graphically. So if this is my function, what I want to graph down here is y prime, or the derivative, or I like to remind myself that that derivative really means the slope. I was just looking for like a number. How many places on this graph, if you were going to point to them, do you know exactly what the slope is? I see some 6s and some 3s and a 0, and I love the honesty. Thank you. 2, great. So when I look at this, there are 6 points where I am 100% sure I know what the slope is. And those are the 6 points where the slope is 0. So right here, if I'm moving along this curve and I'm thinking about my tangent lines, as I move along this curve, right, my tangent line is supposed to kind of match up and look exactly like the curve. Well, when I get to the top of that curve, I know that at least right at the top, the slope of that tangent line is 0. And if I think about tracing this down the other side, then when I get down to the bottom, the slope of my tangent line is also 0 because I hit a horizontal line. So I am thinking about here, 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 and here as places where I know the slope is equal to 0. And because people were giving me some x values, let's get some x values rolling. Well, I'm going to take that 2 pi because I know that we complete one cycle of sine at 2 pi, which means we'd complete another cycle at 4 pi. And I know we'd be halfway in between at pi. And does anybody know what angle we'd be at that maximum for sine? Cool. Someone put it in the chat. I'm looking at pi over 2. And this one would happen at 3 pi over 2. So if I'm copying down my slope, I know that when x is pi over 2, my slope should be 0. And thinking about this graph, because the vertical graph here is my slope, I know that this represents a slope of 0 anywhere up there. So let's figure, so my next slope of 0, well at pi my slope is not 0, but at 3 pi over 2, I do have a slope of 0. And although we didn't work the numbers out for the rest of these, I'm kind of just going to transfer them down. So if I line them up, this one's going to hit here and have a slope of 0, and here and have a slope of 0, and here and have a slope of 0, and over there and have a slope of 0. I guess that one I know is going to be negative pi over 2. Now my next line of defense, right? So first I'm going to label everywhere that I'm 100% sure that I know the slope, meaning anywhere that the slope is 0. The next thing I'm going to do, because our eyes are pretty good at spotting about a 45-degree angle, I'm going to look for anywhere on the graph that I think I've got a slope of about 1. So looking at the part of the graph that I've drawn and thinking about a slope of 1 would be about a 45-degree angle, I'm thinking that right in there, I'm at a slope of about 1. And I'm going to get to that same slope again over here. And I'm going to get to that same slope again over here. So I am looking at a slope of about 1, and a slope of about 1, and a slope of about 1. Well, if I go to translate this down to my picture, if this is a slope of 0, then up here would be like a slope of 1, and down here would be a slope of negative 1. So if I translate those points down, when x equals 0, I was expecting a slope of about 1. So I'll go ahead and give myself a dot there. And over here at 2 pi, so now I need to label another spot on here. There's 2 pi. At 2 pi, I was expecting a slope of about 1. Not going to drag this out too long, but if I'm calling that a slope of about 1, then this slope here at pi is a slope of about negative 1. So at pi, I've got a slope of about negative 1. And I'm going to spare us from doing this everywhere, but I'll do the quick version. Here, I should be at a slope of about negative 1. And here, I should be at a slope of about positive 1. And here, I should be at a slope of about negative 1. And if I kind of connect the dots in a nice flowing way, this would look something like that. And someone clever might say, wait, that looks like cosine. And you'd be right. If my original function is sine of x, the derivative of sine of x is equal to cosine of x. And I'm thinking about, well, what are those slopes going to be? I'm seeing slopes that should be 0. Should be 0 at 0, 2 pi, and pi. So if I were coming down here to write my, if that's cosine of x, and I'm sketching this in, then I'd have zeros at 0, at pi, and at 2 pi. But we're really quickly going to see that it can't be sine, because here at pi over 2, that's going to be a negative slope. So when I go to sketch that on my y prime graph, right, there's my negative slope is actually going to put me down here. And then here at 3 pi over 2, I'd have a positive slope. So that'd be something up here. And it turns out that when we do this, the derivative of cosine is actually negative sine of x. And I've just got time to do it. Well, if my function is tangent of x, then one of those trig rules that we need to know is that tangent is the same as sine of x over cosine of x, which means that if I want to take the derivative of that, we're going to need to use this quotient rule. So I'm thinking about that sine of x as my f and the cosine of x as my g. I want to leave myself just a tiny bit more space here. So when I go to take that derivative, I'm getting myself a nice big denominator, or rather a nice big fraction bar, because I need my 4 parts on the top and the piece on the bottom that's squared. And in terms of this formula, and you really do need to get it memorized, in terms of the formula, this is going to be, we'll have FG, FG, but the F will be primed in the first piece and the G will be primed in the second piece. Now, when I go to take the derivative, so the derivative of F prime, or sorry, F prime is me taking the derivative of sine of x. And our derivative of sine of x is cosine of x. Then I'm going to leave the G alone, so that's still going to say cosine of x. Minus, I'm going to leave the F alone, so that'll be sine of x, and then times G prime. So now I'm looking for that derivative of cosine, which is negative sine of x. And my denominator, I'm just going to take that G, or cosine of x, and square it. Technically, that is a derivative of tangent, but it's not the way that we usually write the derivative of tangent, because we usually use some trig identities to simplify this down a bit. Looking at the top, another way to write cosine times cosine would be to write that as cosine squared x. Now over here, I've got sine times negative sine. So another way to write that would be negative sine squared of x. But because I'm subtracting, the minus and the minus is going to make that a plus sine squared x. And our denominator here is still cosine squared x. And then if we remember back to that fundamental trig identity, cosine squared x plus sine squared x is always, for every angle, equal to 1. So I'd get a 1 on the top, and I'd have a cosine squared x on the bottom, which is also fine, but still not the way that we usually write the derivative of tangent, because if we use another one of those trig identities, 1 over cosine is equal to secant. So the derivative of tangent of x, we usually write as secant squared of x.